Yeah, I would like to thank Professor Xu for invitation. Yeah, and it's very great hospitality. Yeah, I will talk about one conjecture posed by Kosniowski conjecture, and some of the relation to the unitary toric manifold. This is joint work. With my students, Cheng Bo Tan. Yeah. The first, I will give the outline of this talk. The one I would like to sum the notion for the unitary manifold, and the second one about Kosniowski conjecture. The third part, I will give some of the main results. Finally, if we have time, I will explain some of the proof. Yeah, the proof. Yeah. So the first, notion. What is the unitary manifold? Yeah. A unitary manifold. Also called the weakly. Almost complex manifold. A unitary manifold is a smooth manifold, and with a complex structure on the stable tangent bundle. On the stable tangent bundle. That means, there is a map from the stable tangent bundle. That stable tangent bundle that means the sum of the tangent bundle with the trivial bundle. Some trivial bundle, and there is the bundle map J satisfy this map. The square is just minus the identity.
So unitary manifold is not necessarily even dimensional, or is it? Do you still require M to be even dimensional, or just arbitrary?
There are also the older case. Yeah, they just the stable. Yeah, stable case. So almost the complex manifold had the even dimensional case. Yeah. This is the ordinary case, and also we can consider the equivalent case. Here, given a Lie group, we can consider the unitary manifold. With the G action, this effect, this action is effective. If we call, if this action preserves the unitary structure, we will call this G manifold is the unitary G manifold. This is called unitary G manifold. That means this action preserves that's the unitary structure. That means there is the commute diagram. This G. Here, there is a natural action on tangent bundle. Here, the action on this part is trivial. It's trivial action. Yeah, this commute. Yeah. In the special case, if we choose the Lie group, just the torus of the rank n, and we choose the 2n dimensional closed manifold, is effective. This is just a unitary Tn manifold. About this manifold is also the called the unitary toric manifold, introduced by Professor Mikiyamasuda. Yeah. A unitary toric manifold, or the unitary torus manifold. The same, yeah, same. Yeah.
Are you assuming there is, no fixed point, or there's no reason?
Yeah, I'm sorry. Yeah, there are some of the condition. Yeah, also with the condition restricted condition, the fixed point set is not empty. Yeah. This condition is very important. Yeah. In this case, in general case, the fixed point set maybe not isolated, but in this case, because the rank is just half of the dimension of manifold. Yeah, that's yeah, right, yeah, because this action is if reflective, that means there is the injective map from the torus to GL, and this map must be injective. There is injective. From here, you can get the fixed point set must be isolated. Yeah. Then we can give some feeling. The biggest category is just unitary manifold.
The torus manifold is just Tn acting effectively on M2n with non-zero fixed point.
Torus manifold maybe is not unitary.
Not necessarily.
Yeah. Here.
This is more. Is stronger. Than
Yeah. Right. Yeah. We need this restriction condition. This the unitary manifold, and maybe the some parts just unitary, the G manifold, and we have the unitary, the toric manifold, and we have the sum of the parts, the quasi-toric manifold. Yeah, the torus manifold maybe, yeah, I think torus manifold maybe something like this, the torus manifold. Yeah, maybe there are some, yeah. Torus manifold, yeah, I'm sorry, yeah. I think that torus manifold, maybe torus manifold should be contain this part, yeah. Yeah. This is some notions. Now I would like to explain what is the Kosniowski conjecture. Yeah. Around 1917, the Kosniowski proposed the one conjecture. Here, he considered the circle action on the smooth closed manifold. This is just a unitary circle manifold. If the manifold doesn't bound, I'm sorry, there also is some of the condition. The fixed point size is isolated. And then the number of the isolated points.
But not zero, right?
Yeah. Yeah. But if this doesn't bound, it must be this number must be non-zero. And Kosniowski want to know the lower bound about this number. Just the more than the sum the function. This function, the sum.
Equivariantly bound. When you say m bounds, that equivariantly bound or
The ordinary is okay. Yeah.
not equivariantly bound?
Yeah. The linear function.
Than 0.
I'm sorry?
This Fn is strictly greater. Fn is greater than or equal to 0, right?
Yeah, yeah. About this, the function noted by Kosniowski. The most likely this function just the n over 2. This is very, yeah, how to say, I don't know why he just thinks that this function is just this linear function, yeah. But now this conjecture is still open. Still open.
N bound. It does not bound. Why?
But if this function is just this one, and then we can get this number is just more than the. Okay. Right.
I mean, is there any simple? I mean.
Yeah, there is. Now we just have the two-dimensional example. Just a circle equal to a sphere, fixing the two isolated points, and then we have this inequality. Yeah. There are some the related result. Some related result. The one is just by Hadley and the term. Maybe I think that they consider the circle action on the symplectic manifold, not the unitary manifold, just a symplectic manifold with isolated fixed point size and some the restricted condition. And then they show that the number of isolated points is more than or equal to n plus 1. This certainly is more than this one. All right, yeah. this result. Another one, just Li and the Ping Li and the Kefeng Liu. Yeah. Last year, yeah. They consider this one S1, just M2Mn. This is the almost complex manifold. Almost the complex manifold. With also this condition, and then if there is a partition about M partition of the partition of M, such that is the Chen number, the C lambda 1, C lambda R, N, the volume on the fundamental class is non-zero, this Chen number. Then the number of fixed points is more than or equal to n plus 1. Yeah. Now,
is this condition equivalent to the fact that M is not bound?
yeah.
This seems equivalent to the.
Yeah. 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 So, yeah. Recently, we just have this the two related results, but now, yeah, this conjecture is still open. Yeah, unsolved. Yeah.
And the first result, do they have the condition that the M is not bound?
This restricted condition, something, yeah, is a little bit complicated. Yeah, from that condition, yeah, I think, yeah, we should can induce this condition. Yeah, there are some that condition is just for each the fixed point site there are tangent space. Also, we can think that the circle representation and some of the weight. Some of the weight satisfies some of the condition. From there, yeah, I think we should, yeah, get some yeah, some of the. Yeah, Ponchiaki number is non-zero. Yeah. 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 In our case, we will consider the unitary toric manifold. And anyway, about this conjecture here, just the circle action. We also can consider the general case, here just the torus. Torus case, what about the function? What about the lower bound? But in the unitary toric manifold case, yeah, maybe, yeah, we just states our result. In the case of the unitary toric manifold case, we have this result. Here, just a unitary. If we also need to this result, condition, if this one doesn't the bond equivalently, yeah. Doesn't, yeah. It's not corresponding to zero equivalently. Then we can get this, and the number of the isolated points is more than or equal to this number. Here, this means, yeah. This means is the smallest integer, not less than n over 2. Yeah. This is not equal to this number, but is very similar. Yeah, the lower bound.
Oh, it's different.
Yeah, a little bit different. Yeah, here this is not just this one. Yeah.
So let's see. This bracket is the
largest integer, not greater than this number. Here, the smallest, there's something like this number. Here, just this one. This number is just the more than this number. It should be here. Yeah, I'm sorry. Yeah. This results is depend upon the another result about cobordism theory. Yeah. Now I would like to mention another result about unitary toric manifold. Yeah. this is the unitary toric manifold. This the manifold just equivalent is the cobordant to 0 if and only if this the number this the 0 in here just equivalent Chen number. Usually this number is not a really number. It's just a polynomial in here. Yeah. If the here just equivalent Chen class, this one. We just need the only to consider the first and the second the Chen class, the equivalent. Chen class. This is the equivalent Chen numbers. Yeah. Using this result, we can prove that this result about that. I think that we need to mention the background of the cobordism theory. For the I think that's maybe first the ordinary case. Ordinary case, the Mirna and no-equal.
Non-equivariant case, or what do you mean by ordinary case?
Non-equivalent case, yeah. Around 1916, yeah. This shows that unitary the manifold just cobordant to 0 if and only if the all Chen numbers just a 0. And this just the first result. The second one about the ring structure of for all the unitary manifolds. Just this is just this one. This is just polynomial ring. Yeah.
Projecting space.
Yeah. Right. Yeah.
You said
Complex. to S. Yeah.
What is UI? UI is just you're using that as you're writing that as a module. So this graded module.
Yeah, graded module. Yeah.
So U2, U4, U1.
Yeah, yeah.
Generated by X2, X4, X6.
You're right. Yeah. There, for the equivalent case, that case, yeah. For the arbitrary group, there are no any results. For the special case, it was just a torus action case. Yeah, maybe the torus of rank R acting on the. This is not the unitary toric manifold, just the unitary TR manifold. For this case, we also hope to get the similar results, but now there are no we just have a special case result. Yeah. I think maybe in 2002. Yeah. Gilman. I don't know how to pronounce this. Ginsberg and the Carson, yeah. They gave the results in a special case. If we just consider this case. Assume it's just isolated. If in this condition, they show that this equivalent covariance 0 if and only if the O here is just the equivalent the Chen numbers are 0. And then they post the one conjecture for the general case. They conjectured if there are no this condition, this result is still the whole. Yeah. Maybe I think that's GK conjecture. Yeah. There are no this equivalent are 0. Compare with the GGK results. Here, yeah.
So the conjecture is that this point set is not isolated.
Yeah, not isolated in general case. Yeah. Now, yeah, this is just a conjecture. We also can define this theorem in the equivalent case. Yeah, maybe we can write down this torus. But here about this theorem, yeah, let's say it's still open. We don't know anything about this theorem. We don't know anything about this equivalent case, this theorem. Yeah, it's very complicated. Yeah, here, for our result, it's a very special case for this result. This result is this just equivalently correspond to 0. All the equivalent Chen numbers are 0. But for the special case, unitary toric manifold, we just need consider the special number. That's the special number enough. Yeah. Yeah, I think yeah. Next. Yeah, that's the
main reason.
The reason just depend upon the structure of the unitary toric manifold. Yeah, now maybe I need to give some the outline of the proof about these results. Yeah. This some idea of the proof. The first we need to know some of the geometric.
Proof of 2 or proof of 1? Theorem 1. This is a proof of theorem 2.
Yeah.
And theorem 1 comes from theorem 2.
Yes. Yeah. Yeah. Given a unitary toric manifold, and there are some notions maybe, yeah. We need to introduce, yeah, the one closed, connected, codimension 2. Here, that's a real codimension 2 or some manifold of M is called the characteristic if is fixed by some circle subgroup. T. Also, yeah, and contain. I'm sorry. Yeah, okay. It also contains fixed point of the whole Tn axon. Because now we just consider the closed, this manifold just closed. That means we just get finitely many characteristics submanifold, right? Yeah. Here, Mi. We can suppose we just M characteristic submanifold. The O characteristic submanifold. Now, yeah. Now, if we consider the, we choose the one characteristic submanifold, then we can get the normal bundle over this one. Normal bundle. Because each the characteristic submanifold must contain at least one fixed point of the whole Tn manifold. That means for each the fixed point we can get the tangent space, and we also can regard this as this tangent space as the Tn representation, and then we just have about the torus case, the irreducible torus representation must be one-dimensional. Yeah, that means, yeah, that case, this is a characteristic function, this normal bundle. The representation, the one irreducible representation just corresponds to this normal bundle. Then we can write down this one just by this form. Here, yeah. I'm sorry. Yeah. maybe, yeah, I think, yeah. No, yeah. Also, yeah. About this, the number cardinality, just n, right? Yeah. For here, each say I p can determine the elements. I think that here maybe, yeah, I think the first considered mi, yeah, correspond to the elements in H2 torus M. This is just two-dimensional equivalent cohomology, yeah, of M. How to get this corresponds from this inclusion. We can get the equivalent Gaussian map, yeah, equivalent. Gaussian map. And the identity, maybe we just write down the identity element, just one, just map to here is denoted lambda I. This identity element determines only one element. We just get this. Yeah.
This has something to do with the of this MI.
I'm sorry.
MI is a codimensional tool.
Yeah, right.
If you look at this, the Pointelier of this,
Yeah.
you have also a two-dimensional.
Right. Yeah. Actually, in special case, for the quasi-toric manifold case, this one just corresponds to this one, just the generators. For example, if the M just CPN, here there is the n plus 1 characteristic submanifold. That's the n plus 1, just gave the n plus 1 generators. About the, yeah, actually, yeah. Each one can be chosen as generators. Yeah, this one. And then we also can.
That also can be a covariant Euler class.
Yeah.
Normal.
Yeah, right. This one. Yeah. This one restricted the P just to correspond to the this one the Euler class. Yeah. Maybe we this P Euler class. Yeah. From here we can get this one lambda I, the P. This one just form a basis of and this one just basis. Yeah. From here, we can get the equivalent total equivalent Chen class. Just originally this result was obtained by Professor Masta, but it's not difficult to show that. Yeah. By using this one and using the localization theorem by Atiyah, Boltz, and Berlin, regional, about the localization theorem, we can show this result. Maybe do I need to state this localization theorem? Yeah, maybe. Yeah, maybe I need to. Yeah. Here, from here, first, I think that I need to, in our case, I just want to state this result by different way. Yeah. From here, we choose the fixed point. Then we can get restriction about this. That means just we just restrict it to here, and then we just get this one. So only this one. Then we can write down this one, just 1 plus C1 P CNP. This is just an elementary symmetric function. That means for each fixed point, we can get the sigma p collection, just CP1 p, CPNP, right? Yeah, and then Now we can write this one. Sigma p belong to mt. Maybe there are the different fixed point sites with the same this collection. Yeah. Here we just write this sites just sigma 1 sigma t. And then yeah, maybe we also need to implant some and then we just write this number. This number is just this number.
So this small t is the number of its points, or what do you mean? What is the indication?
This means
Small t is just the number of its points, or?
Small t means the number of the difference is the if we temporarily we just forget this part about this set, maybe for the different fixed point set, maybe corresponding are same, right? Now
You choose all different.
all the difference, yeah. This one, sigma p, just sigma l, sigma l. This tangent space. Here we also can think this tangent space is just a normal bundle over the fixed point. Then we have the Euler class. This Euler class just the minus or plus the sigma n l. Here we just consider maybe we just consider the plus this case, or also this number just this number of the fixed point set the minus this number. I'm sorry. This one. And then we can state the Thibaut's Berlin and Virginia localization theorem. For the here omega just I1 IR just the multi here we just consider equivalent chain numbers. this usually is not the partition of the dimension of manifold. The arbitrary is the partition of arbitrary integer. Yeah, this number is just this one. Sigma 1 P I1 sigma and then we can write this one. This sigma, I think, yeah, sigma 1 L. Is this one. The next, I think, yeah, maybe we just give some the key points about this proof. Yeah, we just use this formula. There are some the key points. The one point, the P and the Q and MT, we can get this result. Sigma P and sigma the Q, and if and only if sigma 1 P, sigma 1 Q, and sigma 2 P and sigma 2 Q. We can show that this result. That's the reason the why we just need needs only the first and the second Chen class. Yeah, that's the reason. We can this one. After this results, and we can use.
That's not in general true for every elementary symmetry functions, right?
Yeah.
You just apply this to this particular P and Q.
Yeah.
Which is
this is general case for an arbitrary the two fixed point
well,
set.
What I'm saying is just for elementary symmetric functions.
Yeah. This one just from the CT TPM, we can get this one. Yeah. And then yeah.
I mean, in general, symmetric functions or elementary symmetric functions is not determined by first and second.
Yeah, right. Functions. Yeah.
But you especially apply this to P and Q, then they are determined by
first and the second. Yeah. But in the toric unitary toric manifold. This is the one of the key points. Another one, by using this localization theorem, we can get the when there, then the matrix, we can choose the special things. Finally, we can determine this number, which must be 0, and then we can show that. Yeah. I think that this is just a key point. Yeah.
And then your theorem follows from the previous results by.
From this result, we can get the corollary results, and then we can get the theorem 1. Yeah, and this maybe. Yeah.
This theorem 2
Yeah.
follows from this key observation.
Yeah.
And Ginsburg questions work, or
About
Ginsburg questions work that.
this result just here just all the equivalent Chen numbers.
Right. So all the covariant Chen numbers are 0.
Yeah.
Then this manifold is covariantly coordinate to the boundary.
Yeah. Yeah.
That result is what? Ginsburg? No?
Yeah. Yeah. Right.
Right.
Yeah. Yeah.
You are appealing to the Ginsburg.
Yeah.
Ginsburg questions work.
Yeah. Also, we can use. Yeah. They also just use this localization theory to prove their result. Yeah. Here. Yeah. Yeah.
Oh, you mean this? Yeah, Ginsburg question used idea about
Yeah.
this theorem,
Yeah.
Berlin and what's his name?
Wegener. Wegener. Attia bought Berlin and Wegener. Wegener. I don't know. Yeah. Yeah. How to pronounce? Yeah.
So just you can't you just say using this key point
Yeah.
plus Ginsburg questions work, because Ginsburg questions work are for any TR action with isolated point, fixed point.
Yeah.
And you have all the covariant Chen numbers are 0.
Yeah.
Then they are covariant covalent.
Yeah.
But you have this more restricted case.
Yeah. Yeah.
But you only assume first and second Chen class
Yeah. Yeah.
using the covariant Chen classes.
Yeah.
Chen numbers, you
Yeah.
those two, then they are covalent,
Yeah.
right? So
Yeah.
your observation is that this first and second
Yeah.
actually gives all the covariant Chen numbers.
Yeah.
So maybe, I mean, that's what I'm basically philosophically, that's the main idea, or do you?
How to pronounce it? Yeah. This result is just a result in special case. Right. Of the Gilman and Carson results. Yeah.
So to prove this, do you actually need this Attia-Bott Berlin
Yeah.
localization theory?
Yeah. We also can use the Gilman and Gilman Carson result. This way is always very easy. This direction, but this direction.
But Gilman Carson work is also in both ways, right?
Yeah, both way.
So my question is,
Yeah,
without appealing to ABBV, this localization theory,
yeah,
just appealing to key points
yeah.
and Galenin.
No, the only use this result, and this key point, we can show that this result. We also can apply the Gilman result.
So without applying localization theory,
Yeah.
we can apply to Ginsburg.
Yeah.
Yeah, right.
Yeah.
That's my question.
Yeah.
But they are using ABBV localization
Yeah,
theory
right.
to prove them.
Yeah.
So without appealing to their theorem, we can directly prove.
Yeah.
Yes, that's right.
Yeah.